Welcome everyone to our Scaling Networks class. Today we're going to be discussing Chapter 6, which is about EIGRP. Now, before we start discussing about EIGRP, let's actually have a look at what we did last week, just as a quick review. Now, last week, if you remember, we actually designed a simple network topology. We had a few routers, a few switches. We also said that we had a few networks as well. So every single one of these circles with different colors, they're just basically different networks. This is network A. The second one here is network B. We also have network C. Now I added this here since our last class. And this is just basically to simulate what we would expect to find in a real world environment. Now we have a connection to the internet. We have an ISP router here on the top, which is router 3. And we also have router 2 and router 1. All right. Now, last week we discussed about dynamic routing protocols and the importance of dynamic routing protocols, which is to basically inform all the routers about all the networks that are in the network topology. So here we have network A, network B. We have a network which connects router 1 to router 2. Now, last week we discussed about all the networks that router 1 knows by default. Can anyone tell me which networks does router 1 knows by default? If I haven't configured any dynamic routing protocol in this network topology, what are the networks that router 1 knows about? Anyone? Yeah, so router 1 knows about all the directly connected networks to itself. So that basically means that router 1 knows about network A, it knows about network B, and it also knows about this peer-to-peer link, which connects router 1 to router 2. Now, how about router 2? What are the networks that router 2 is aware of? Anyone? I'm going to give this network a name, this network which is in pink, peer-to-peer to the internet. Now, what are the networks that router 2 knows about? Anyone? Without any configuration? Router 2 knows about network C, network peer-to-peer, which is the one in blue, and also about the purple network, which is the peer-to-peer to the internet. Now, we said that if we wanted to make sure we can ping from network A to network C, because it crosses two different routers, we need to make sure router 2 learns about the network A, and we also need to make sure router 1 learns about network C. Now, last week we discussed two methods that router 1 can learn about network C and that router 2 can learn about network A and network B. Now, for instance, we have two approaches. We have the static routing approach, which is just basically going to be discussed in routing and switching in the end of the semester. And we also have the second approach, which is using dynamic routing protocols. Now, we discussed a few dynamic routing protocols last week. We talked about the external gateway protocols, exterior gateway protocols, interior gateway protocols, so EGPs and IGPs. Now, we said that IGPs, they are used internally, so they're used inside of the network and inside of the same autonomous system. And we also have EGPs, exterior protocols, which are used in different autonomous systems. Now, today we're going to be discussing about one of the interior gateway routing protocols, which is EIGRP that we talked about last week. So let's move on to our presentation. So we are going to talk about the EIGRP characteristics. We are going to explain the features and characteristics of EIGRP. In other words, we are basically going to describe how EIGRP works, the basic features, the type of packets used in EIGRP. We're going to describe the encapsulation of an EIGRP message, and then we're going to move on to discuss how we do the EIGRP implementation for IPv4 networks. We're also going to discuss about EIGRP operation in a small to medium-sized business network. we are also going to implement EIGRP for IPv6. Okay, let's get started with the first topic of the week, which is EIGRP characteristics. Now, EIGRP is an enhancement to the IGRP. So the original standard was called IGRP. It was a Cisco proprietary distance vector routing protocol released in 1992. So Cisco created EIGRP. However, Cisco actually opened the standard in 2016. So a little bit over 5 years ago, Cisco decided to release to the public. So it basically opened it up to the ITF to take care of it. So now it's supported across a multitude of vendors as well. It doesn't necessarily need to be Cisco. Now we have a few features of the EIGRP protocol. Now EIGRP uses an algorithm in order to calculate the best paths. We discussed about this last week, but basically when we have multiple routers, when they want to learn about multiple networks, there might be multiple paths from one router to reach another router. Now, EIGRP uses this algorithm called dual in order to guarantee that a path is a loop-free, and it can generate backup paths as well in order to reach a destination network. Now, EIGRP also establishes neighborships. In other words, when it starts talking to another router which is also configured with EIGRP, they basically become friends. And when I say that they become friends, that just basically means they are now aware of each other. And then we call these the neighborship establishment. When they become neighbors, they basically know about each other's existence, and they can just basically proceed to exchange information. They can just basically talk to themselves. EIGRP also uses something called the Reliable Transport Protocol in order to make sure the delivery of the messages is reliable. And it just basically does that by using acknowledgements. So it sends a message between neighbors. So when it wants to tell a neighbor about a network, it will send the message, but it will also request an acknowledgement. And when it does that, it just basically does reliable transport of a message. And thus it uses the RTP protocol. It also does partial and bounded updates. Now, we discussed about RIP last week, one of the routing protocols. RIP is just basically a routing protocol that will send updates periodically. So that just basically means it will send information between the routers every 30 seconds, as we discussed. Now, EIGRP is slightly different in a sense that EIGRP does not send periodic updates. EIGRP will just send an update message to another router once something is detected. So once a new network is added, or once a network cannot be reached anymore, that's when an EIGRP router will send an update to another router. EIGRP also supports equal and unequal cost load balancing. Now, when we discussed about RIP, if we had multiple paths from one router to another router, RIP would choose the best one, the best path. And it will choose the best path based on the number of hops. In other words, if it has fewer routers from the source to the destination, you will just choose the path with fewer routers to send the message. Now, EIGRP supports these two things, the equal and unequal cost load balance. And that just basically means if we have multiple ways to get to the destination, EIGRP can use multiple ways at the same time. Equal would be sending the same amount of packets in both links. Unequal cost would be sending more packets into a certain link depending on the link bandwidth, for example. So if certain link has higher bandwidth, you can send more packets, of course. If another link is lower bandwidth, you can still take advantage of the link, but in other words, you just send fewer packets in that link. Now, one interesting thing to note is that EIGRP is one of the only protocols that support this feature called the unequal cost load balancing. So this magic thing of sending more packets where we have more bandwidth or where we have a better path but you can still send packets to the worst path, can only be found in EIGRP. So we don't have these features pretty much anywhere else. It's not available in RIP. It's not available in OSPF. It's not available anywhere except EIGRP. Now, EIGRP uses protocol-dependent modules to support different protocols. In other words, EIGRP will support IPv4 and IPv6. Now, it's the same way of thinking. If you have separate networks, the routers will only know about the networks that they're directly connected to, and this principle applies to both IPv4 and IPv6 networks. Now, EIGRP can support both IPv6 and IPv4. It just basically keeps everything separate. So you have a separate neighbor table for IPv6, a separate topology table for IPv6, and a separate routing table for IPv6. So it basically separates everything according to the network protocol, if it's IPv6 or IPv4. Now, RTP, which is the reliable transport used by EIGRP, is a transport layer protocol used to deliver and receive EIGRP packets. Now, not all RTP packets are sent reliably, so some of them will actually not require an acknowledgement. For example, a hello packet. A hello packet doesn't require an acknowledgement. Another packet that does not require an acknowledgement is the acknowledgement itself. You don't need to acknowledge an acknowledgement. Now, all the other packets, the update, the query, the reply, and we're going to talk about each one of these packet types in a few slides, but they all require an acknowledgement. So if you send an update to another router, you expect to receive an acknowledgement from the other router saying that the other router has received the information. Now, EIGRP supports authentication as well. Now, when we talk about dynamic routing protocols, one thing that may come to our minds is that if the other router is actually a router which is a rogue router, in other words, it's a router that doesn't belong to someone we trust, we don't want the other router to establish a neighborship with our router. So in order to prevent this from happening, we can protect the connections, the neighborship establishments with a password. Now, just using a password is not enough. And because it's not enough, we need to find a way to transfer the password or the message with the password in a way that if someone intercepts the message, they will not be able to look up into the packet and find out what the password is. Now, in order for us to do that, we do something called a hashing. So we take the password, we hash the password using a hashing algorithm that could be MD5 or SHA. And with these two hashing algorithms, the password that we're going to be transmitting with the hello message to the other router to establish the neighborship will not be able to be unencrypted if someone doesn't know what the password is. Okay. Now, EIGRP supports both hashing algorithms, SHA and MD5. Now, EIGRP relies on 5 types of packets to maintain its various tables and establish complex relationship between neighbor routers. Now, these are all the message types that we have in EIGRP. We have the hello packet, which is just basically a message that a router sends to another router saying that it exists and it wants to become a friend with the other router. The update message is a message that a router uses to send updated information. So information about a new network, information about a change in a network that already exists. We also have the acknowledgement, which is just basically the fundamental of the RTP. It just basically acknowledges that a certain message was received. We also have the query, which is a request for a specific information. And we also have the reply, which is a message that the router sends with a respond to a query message. So if you ask me a question, I'll respond back to you. If you ask me a question that most likely going to be a query, I'll process the query and I'll reply back with the message of whatever it is that you want to find out. Now, how does the hello messages work. Now, imagine we have these topology here. We have three routers, router 1, router 2, router 3. Now, if we configure all of these routers with EIGRP, they are now able to send these hello messages. Now, if they have been configured with the same autonomous system number, they are pretty much aware of themselves. They can talk to other routers that are using the same autonomous system number. If they are all in the same autonomous system number, they can then start exchanging a few messages. On hearing hellos, a router creates a neighbor table. So once a router contacts another router successfully, it will just basically register the other router as a neighbor. And this is going to be saved into something that we call the neighbor table. Hello packets, they are all sent unreliably. In other words, they are not required to have an acknowledgement. You send a hello message. If you receive another hello message from another router, that means it's all good. You can form a neighborship with another router. Hello messages, they are exchanged periodically. So every once in a while, a hello message is sent just to make sure that the other router is still alive. Now, don't get confused here. The hello message is just to make sure the other router is still alive. It doesn't mean that EIGRP is doing periodic updates, because as we already seen, they don't do periodic updates. It's triggered updates. So the updates are only happening if they're necessary. Now the hello messages, they're always happening just to make sure the other routers are still alive. We have a timer for these hello messages. If it's a slow link, which is less than 1.5 megabits per second, it is just basically going to happen every 60 seconds. And if it's a link which is faster than 1.5 megabits per second, it's going to happen every 5 seconds. Every single one of the routers, they also have something called the hold time. The hold time is by default 3 times the hello interval, and the hold time is just basically the amount of time that the router will wait until it considers that the other router is dead. Okay? If a router considers that the other router is dead, it just basically considers that it has been a disconnection to the other router. It's not able to talk to the other router anymore, and will just basically stop communicating with that router. EIGRP uses multicast in order to exchange messages, and unicast rather than broadcast. So we have no broadcast messages. So router 1 will not send broadcast messages to all the routers here. It will actually send a multicast message. So once we configure a router to be EIGRP, we are just basically telling the router to start listening to messages which are in the EIGRP multicast IPv4 address, which is the 224.0.0.10. So once a router becomes a multicast group router of the IP address 224.0.0.10, it will accept the hello messages. The hello messages, they are messages sent to every single one of the routers which belong to the multicast address 224.0.0.10. If we are running IPv6, it's basically going to happen with the IPv6 address FF02::A. This is going to be the multicast address for any router which is listening to EIGRP messages in IPv6. How about the updates? So EIGRP update packets, they are used to propagate routing information. So once something happens, once there is an event, once there is a new network in the router itself, once we configure a new network to be advertised using EIGRP, the router will send an update. In this example here, router 2 is actually losing a connection to a LAN. So router 1 had a LAN connection as represented here, and after this connection is lost, router 2 doesn't have any route to this network anymore, and it basically needs to tell every single one of the other routers it doesn't have a path to this network anymore. And this is done by using an update message. Router 2 will send a triggered update message once the network is down to every single one of the other routers in the EIGRP autonomous system number. These update, as we already seen before, they need to be acknowledged. So every single one of the other routers will send a message back to router 2 saying that they have received the message, and now they're pretty much aware that network that was lost cannot be reached through router 2 anymore. How about a query message? Query and reply packets, they are used by Duo when searching for networks. Now, once the local area network in router 2 is disconnected, once this network goes down, all the routers in the EIGRP autonomous system number, they need to try to find another way to the network that was lost. And they do this by sending a query message. Now, a query message is a message sent to all the routers again, asking if there is an alternative way to reach the network that was lost, the network that became down. So all the routers, they will try to find another way, an alternative way to reach the network. And this is done by sending a query message. Now, once a query message is sent to all the routers will reply back if they have a response. If they don't, they reply back saying they have no way to reach the destination network that has been queried. There's a nice video for you guys to actually that actually demonstrates a Wireshark output for EIGRP. It will just basically displays the packets that are related to EIGRP communication between the neighbors. EIGRP message. Now, as we already seen, EIGRP message is a message that is sent to all the routers in the 224.0.0.10 multicast group address. Now, when we are talking about these 224.0.0.10, that is going to be the destination IP address of the EIGRP packet, but we also need to have a destination address for the frame of the EIGRP packet. In other words, we also need to build a frame, and we also need a destination address for the frame itself. It's going to be a MAC address, and this MAC address is the 01.005v0000A. That is basically what's going to be the destination MAC address for all the routers that are participating in the EIGRP process. Now, once we build this IP packet, we also need to have a way to identify that this IP packet belongs to a specific routing protocol, and that is done by using the protocol field. The protocol field value is set to 88. So once the protocol field is set to 88, every single one of the devices that look up this packet, they will be able to tell that this information is actually an EIGRP packet. Now, EIGRP messages include the header with an opcode field that specifies the type of EIGRP packet. So the opcode field, which is located in the IP packet itself, is basically going to tell what type of EIGRP message we are sending. If it's a hello, if it's an acknowledgement, if it's an update, it will just basically tell us based on that code. You don't need to know all the codes, you just need to know how they work. You just need to know that you can find out that information based on the opcode field of the packet. Okay, now that we discussed how EIGRP works, we discussed about how routers communicate to themselves, how they create these friendship called the neighborship. Let's discuss about how do we finally implement EIGRP. We have an example here that we're going to be studying. The routers in the topology, they all have a starting configuration that include addresses on the interfaces. So every single one of these routers, they have already been configured with the basic settings. So router 1 already has all of its interfaces configured with an IP address according to the topology shown. However, we need to be aware that they only know about the networks that are directly connected to them. Pop quiz question before we get started with this. Can anyone tell me about the networks that router 2 knows about? Can you type the answer in the chat? what are the networks that router 2 knows by default. So once we configure the interfaces on router 2 with an IP address, what are the networks that router 2 will know about? What are the networks that I'll be able to see in the routing table of router 2? Anyone? Come on guys, answers. What are the networks that router 2 knows about once I configure router 2's interface IP addresses? Anyone? Yeah, we got some answers coming. Okay, so let's have a look at this. Now, what are the networks that router 2 knows about? Basically, all the interfaces that we have configured in router 2. So once we configure an interface of router 2 to be gigabit 0000, and we configure this IP address for interface gigabit 00, it's going to be known by the router. So router 2 knows about this network, it knows about this network, it knows about this network, and it knows about this network. Congratulations if you got the answer correct. Router 2 basically knows about all of these 4 networks by default. Now, can anyone tell me if router 2 knows how to get to the internet? And can anyone tell me if router 2 is able to reach the LAN connected to router 1 and the LAN connected to router 3? Does router 2 knows how to do that by default? Yeah, it doesn't know how to do that, and that's where we're going to be needing a dynamic routing protocol. In this case, we're going to be using EIGRP in order to exchange information. So in order for router 2 to be able to contact the LAN connected to router 1, we need 2 things to happen here. First of all, we need to find a way to reach the LAN connected to router 1. And according to the diagram here, we actually have 2 ways of doing that. So router 1 can go this way, router 1 can go router 3 first, and then back to router 1. So there are actually 2 ways that router 2 can reach out to router 1. Now, if my router 2 knows about these LAN connected to router 1, that is not yet enough. And that is because router 1 still needs to be able to know about router 2's existence. If router 1 doesn't know about the LAN connected to router 2, it won't be able to reach the LAN connected to router 2. So in order to make sure every single router knows about every single other router's existence, we need to configure dynamic routing protocol on all of these routers to make sure they will be able to tell themselves what are the networks connected to them. And we're going to do this right now. So just a quick reminder of what an autonomous system is. An autonomous system is a collection of networks under the control of a single authority. So if we are all managing all the devices, if all the devices they are under our control exclusively, we can say that we are an autonomous system number. For example, different companies, they are a different autonomous system number. Now, if they merge and if there's only one person that can manage all the devices within that network, we can say they're in the same autonomous system number. Now, autonomous system number is basically related to the concept of who is managing the devices. Under whose control are the devices? Who is controlling all the devices? Now, autonomous system numbers, they are numbers which usually range from 0 to 65,535. It's a 16-bit number, and autonomous system number, they were actually increased to 32 bits as well in the extended range. Now, this is just a few numbers that we can give to our autonomous systems. To configure EIGRP, so let's follow up these steps if we want to make sure 2 routers can communicate and they can tell themselves about the networks that are connected to them. In order to do that, the first step is we need to configure EIGRP on a router. In other words, we need to enable EIGRP. And we do that with the command router EIGRP, and we specify an autonomous system number for that EIGRP protocol. Okay, it's not good to configure multiple instances of EIGRP on the same router, so we're always going to try to keep it to one so that all the routers they are in the same autonomous system number. So all of these routers, they are managed by the same organization. They are in the same autonomous system number. We cannot manage this one. Let's say this one belongs to the ISP. So all the routers we're going to include in the same autonomous system number, and all the routers we're going to be able to exchange routes are router 1, router 2, and router 3. Once we enable EIGRP with the command EIGRP router, router EIGRP, and then we specify the autonomous system number. Once they are in the same autonomous system number, we need to make sure we find a way to differentiate the routers. So we have different routers. There has to be a way we can identify which router is which router. Now, this is done by the router ID. The router ID is a 32-bit number, and it can be written in the IPv4 address format. It doesn't mean this is a valid address. It just means that there is a way for us to identify the router with this thing called the router ID. The router ID looks like an IPv4 address because if we don't configure the router ID manually with command router ID, the router will assign itself a router ID automatically based on the loopback interface which is active and the highest IP address if there's no loopback address on any active IPv4 interface. In this example here, we actually have the scenario where the router ID is not configured in router 1. So router 1 needs to assign itself a router ID. Because we have no loopback interface, router 1 will look up on all the interfaces that are physical interfaces. So router 1 will look up this IP address, this IP address, and this IP address. The highest IP address will become the router ID. Now this router ID is only significant for the EIGRP process. That's it. It has no more meaning except that is a way to identify what router is what router in the EIGRP configuration. That's all. In the example that we had, we can also assign a router ID if we don't want the router ID to be assigned automatically. Now, if we leave the router ID to be assigned automatically on every single one of the routers, router 1 will give itself the address 192.168.10.5 because that's the highest IPv4 address on an interface which is up. And because it doesn't have a loopback interface, it will be the interface with IP address 192.168.10.5. Now, if we leave for the router to assign itself a router ID on router 2 and router 3 as well, router 2 will assign itself the following IP address, and router 3 will assign itself the following IP address. If you have a look at them, they are all the highest IPv4 address on an active physical interface. Ideally, we don't want to let the router assign itself an IPv4 address because it makes things a little bit harder to identify the routers. I particularly don't like to do that. So in my case, I always like to assign the router a router ID. Usually what I do is I assign router 1 the all ones address. Okay. Remember, this is not an IPv4 address. This is just a format. It's not significant as an IPv4 address. It just looks like an IPv4 address. So you can pretty much assign any value that you wish as long as it's the dot notation that looks like an IPv4 address. Cool? So that's all you need in order to assign a router ID. So what I usually like to do, I like to assign the all ones router ID to router 1. You can assign the all 2s to router 2, for example, all 3s to router 3. It's basically up to you. Now, after we configure EIGRP, now we know how to identify the routers with the router ID. We know that the router ID can be configured manually. We know that the router ID can also be set by the router itself automatically. We need to find a way to advertise the networks. Now, by default, the router will not advertise anything. In other words, the router will not tell another router about anything. So we need to specify the networks that we want our routers to communicate to other routers. After we configure EIGRP, we need to tell what networks we want to advertise. In other words, we need to tell the networks that we want our routers to tell the other routers about. And we do that with the command network, and we type it in the network address. Now, if we don't include the subnet mask, what is going to happen is that it's going to match the interface which contains that network address. We can also specify the wildcard mask. This is optional. If we specify the wildcard mask, we actually have something which is more precise. So we can activate a precise interface. A quick one, what is a wildcard mask? So for some of you guys, this is going to be a review. For some of you, it will not. A wildcard mask is just the inverse of a subnet mask. So in order to find what the wildcard mask is, we take the all 255 addresses and we subtract the subnet. And that's how we find the wildcard mask. I'm going to do an example here because people are usually confused about this. Now, you see wildcard masks pretty much everywhere. Wildcard masks, they are usually used when configuring routing protocols. So when we configure EIGRP, when we configure OSPF, when we configure ACLs as well, access control lists, they all require you to know the wildcard mask. The wildcard mask is easy to be found. It's just a matter of finding out what the subnet mask is. For example, if I have a subnet mask which is /24, are we able to then determine what the wildcard mask is? Yes, we are. So the first step is translating the /24 to a decimal notation. Does anyone know what the decimal notation of /24 is? Anyone? Yep, thanks. It's the 255, 255, 255.0, right? Now, if we want to find out what the wildcard mask is, it's just a matter of taking the all 255 addresses. So for example, 255 everywhere, and subtracting the subnet mask. And that's how we find the wildcard mask. So in this case, what is the wildcard mask for this address? Sorry, I'm missing a 5 here. So what's the wildcard mask, guys? So the wildcard mask for this address will be, this is 0, 0, 0, 255. And this is how we find the wildcard mask. Okay. So once we specify a network for EIGRP, we actually need to specify it using the wildcard mask. In this example here, we're actually trying to advertise these two networks. One of the networks is network 192.168.10.0. Now we can specify it using the subnet mask, or we can also specify that using the wildcard mask. Now, if you enter the subnet mask on the latest Cisco iOSs, they will actually translate that into a wildcard mask by default. In this example here, I've actually configured EIGRP using the subnet mask. As we can clearly see here, when I do a show running config, my Cisco iOS has actually changed the subnet mask to a wildcard mask. Now, when we talk about EIGRP, we also need to talk about the passive interface feature. The passive interface is basically going to tell the EIGRP process that a certain interface should not be participating in EIGRP whatsoever. In other words, do not send any hello message to a specific interface. This is a useful command if you know that a certain router interface is not going to be connecting to another router, but it's always going to be connected to a local area network. You don't need to send EIGRP messages to a local area network because you have no other router in the local area network. So in order to make sure this is not going to happen, because after all, EIGRP will just consider that it can send hello messages on all the interfaces. In order to prevent this from happening, we can use the command passive interface. With the command passive interface, we are just going to specify the interface which is going to be connecting to a network that won't have any other router. Once we do that, the router will not send a hello message out of that interface. We also have the passive interface default. Passive interface default will tell the router to set all the interfaces to passive by default. In other words, if we configure a router with the passive interface default, we need to specify which interface we want to send hello messages for EIGRP. So if we enter the passive interface default on the router, all the interfaces will be excluded of the EIGRP process, and then I will have to specify which interface I want to be part of the EIGRP process, and I will do that with the no passive interface, and then I'll specify the interface that I don't want to be passive. All right. Now, how do we verify EIGRP functionality? Now, EIGRP can be verified with the command show IP EIGRP neighbors. That is going to display us every single one of the neighbors we have in a specific router. These router here, for example, router 1 will have two neighbors. One neighbor is 192.168.10.6 and the other neighbor is the 172.16.3.2. Keep in mind this is actually the neighbor's IPv4 address. It's not the router ID. So this is the address of the actual router. We also have the interface that is used to reach the neighbor. We have the hold time in seconds, so the amount of time it's still going to be waiting for another hello. We also have the uptime of the neighborship, so how long they have been friends for. And we also have some other information about the packets themselves. We also find out information about the dynamic routing protocol on our router with the command show IP protocols. One of the most useful commands when troubleshooting dynamic routing is this show IP protocols command. It will show us which routing protocol we are running. It will show us the router ID. It will show us the administrative distance, the gateway address. It will show us every single one of the neighbors' IP address, the distance, and so on and so forth. Now, I'd like you guys to have a quick look at this definition in 3. It says that the EIGRP administrative distance on router 1 are 90 for internal routes and 170 for external routes. Now, the administrative distance, guys, this is a number to tell which route is better. So if we have multiple routing protocols configured, so for example, if I have RIP configured, EIGRP configured, OSPF configured, and we are exchanging information between all the routers using all these different routing protocols, that is possible. However, just one of the routing protocols will be able to install a route in the routing table. And that choice of which one of the routing protocols will install a route in the routing table will be done based in the administrative distance. Administrative distance is a number which goes from 0 to 255, and every routing protocol has a different administrative distance. EIGRP uses 90 for internal routes and 170 for external routes. OSPF uses 110 and RIP uses 120. So the lowest one will be the one that will always be chosen and the one that will be installed. So if we have all these routing protocols installed, running, the one that is going to actually tell us where to go will be EIGRP, because EIGRP has a lowest administrative distance. So the administrative distance will tell us which routing protocol we should trust more. Cool. Now, if we run the show IP route on every single one of the routers after configuring EIGRP and telling them to exchange the routes, we'll be able to see that in the routing table now we have information about D. D is a route that was learned by EIGRP. Okay. C is connected networks, L is the local interface, and D is the EIGRP network. So it was learned from another router, a neighbor router. Now it's D. I know D doesn't sound like it's too much intuitive, but if you remember that EIGRP uses dual algorithm, you will understand why we have D in the routing table. Now, this router 1 actually learned about how many routes. So it learned about the 172.16.2. So it learned about this one here on top, which is connected to router 2. It also learned about the 1, which is connected to router 3. It also learned about the 10.8, which is just basically this one here as well, which is not directly connected to it as well. In other words, router 1 just basically learned about pretty much everything else except the one that goes to the internet. If we have a look at router 2, we'll see that the same thing had happened. Router 2 has learned about the LAN connected to router 1 using EIGRP. It also learned about the route connected to router 3 through EIGRP. And if we have a look at router 3, we'll see that router 3 has learned about all of these networks that were not directly connected to it using EIGRP once again. Now that we have a route in the routing table, we basically have the information that we were missing. Remember when we discussed about the routing table? The routing table contained entries about networks and how to get there. So let's have a look at router 1 again. So let's take 172.16.2.0 for instance. That is basically the network connected to router 2. Now we have the information for router 1 how to get to this network. It just basically needs to go through 172.16.3.2, which is just basically the IP address that it needs to take to reach router 2 LAN. Okay, and it needs to go out of interface 0000. Okay, so router 1, if you want to go to that LAN, take your serial interface 000 and go out this network, and you're going to be able to reach out that specific network. There is a packet tracer activity for you guys to do to verify EIGRP with IPv4. So basically going to observe how the EIGRP routes are going to be learned. So router 1 is expected to learn information about R2 LAN, R3 LAN, and this network which is not directly connected to it. So if everything is configured correctly, you'll be able to see that every single one of the routers will learn about all the networks that are connected to all different routers. There's also another lab for you guys to do. This would be more a physical lab. You can also try to do this one in packet trace as well. It would just basically be pretty much the same thing. EIGRP operation. Router 1 has joined the EIGRP routing domain and sends an EIGRP hello packet out EIGRP enabled interface. This is basically the initial communication process that a router will do with another router once they have been configured with EIGRP. So one router sends a message to another router will tell the other router that they want to talk as well. In this case here, we have router 1 sending a hello message. So it's just basically saying, hey, I'm a router, I want to talk EIGRP. If you talk EIGRP, let's just communicate. And then router 2 will send, here's my information. I also want to do EIGRP communication, so let's just exchange information. And that's when they establish the neighborship. Now, router 1 adds all update entries from router 1 to its topology table. So once it obtains information, they exchange information. They will add this information that they obtained from a different router into this table called the topology table. Topology table will be a table that contains the information that the router has just collected using the EIGRP communication process. Routers, they all use the dual algorithm, as we already discussed. The dual algorithm calculates the best routes to reach a destination route, including the metric, the next hop router, and updates its routing table with the best route. So this topology table is built with the information that we collect from every single one of the other routers. Once the topology table is built, a router is then able to calculate the best paths to reach a certain network. And it does that using dual. Dual is just basically an algorithm that calculates mathematically a value, and then it will take the best path based on the value that it calculated. We're going to see how the router calculates the best path in a few slides. EIGRP uses a composite metric to calculate the best paths. In other words, just basically a mathematical formula, and it just basically takes into consideration the bandwidth of the link, the delay, the reliability, and the load as well. So all of these parameters, they are just basically thrown into the formula. You don't need to know the formula, all right? You just need to know that the formula exists and what are the factors that the formula calculates and what are the factors that the formula takes into account. The bandwidth, the delay, the load, and the reliability. Now there's a command for us to change the metrics. The metrics, they are associated to every single one of the parameters that are used to calculate the metric and to determine who is going to be the best path. Now, in order to verify what are the parameters configured on a router, we can execute the command show interfaces serial. And then we're going to be able to check every single one of the parameters of the metric that EIGRP is going to calculate. EIGRP metrics, so we can actually change some of the metrics of EIGRP in order to manipulate who is going to be the best path or who is going to be the worst path based on the formula. One of the things we can change is the bandwidth of a link. We just need to go to the interface configuration of the link, and if we type it in the bandwidth and specify the kilobits, we'll be able to change the bandwidth manually. Now, obviously, you're not going to be able to change the bandwidth to a higher value than the bandwidth, okay? So if we have a link which the maximum bandwidth is already 1.5, you are not going to be able to change with a command the limitation of the physical link. Okay? So you can set it to a lower value if you wish. You're not going to be able to set it to a higher value than the maximum amount of the bandwidth of the physical connection. In this example here, we actually manipulating the bandwidth on the serial links. By default, all the serial links, they are T1 link. They are 1.54 megabits per second. Now we're just changing the bandwidth between router 1, router 2, and router 2 and router 3 to manipulate the calculations and to manipulate what is going to be the best path. Delay is another thing that is considered. The delay is the measure of time it takes for a packet to traverse a route. The delay is the metric that is not measured dynamically. Now, the delay is just basically the amount of time that it takes for a packet to traverse the link, the network. The delay is calculated using the cumulative delay of every single one of them interfaces until we reach the destination route. The delay is the measure of time it takes for a packet to traverse the route. The delay metric, which is the DLY, is not measured dynamically. It is a static value measured in microseconds, based on the type of the link to which the interface is connected to. The delay value is calculated using the cumulative sum of all the interfaces that we discussed already. Now, for every single one of the types of links of Ethernet media, for example, gigabit Ethernet, fast Ethernet, there is a certain delay associated with every single one of them by default. We can determine the EIGRP metric with the formula as follows. Once again, we don't need to know the formula. I know it's pretty hard to remember all the components of the formula. We just need to know the basic things included in the calculation. We don't need to actually know how the calculations are done. Now, we have two types of metric. We have the composite metric, which just basically takes the bandwidth and delay into account by default. So by default, EIGRP will just consider the bandwidth and the delay of the link. If you want to include other stuff in the calculation, you actually need to configure that manually. But by default, EIGRP will only consider the bandwidth of the link and the delay of the link as well. Now, how does this dual algorithm works? It works based on the calculation of the metric. So once the topology table is built and once all the metrics are calculated by the router will basically then analyze every single one of the entries in the topology table. Now we need to know some definitions of the routers involved in the EIGRP process. We have the successor, which is a neighboring router that is used for packet forwarding, and it's the best choice based on the metric. So once the topology table is calculated and a metric is found for all the paths that we can reach a network, EIGRP will consider a route to be the successor route. In other words, the best route. The feasible successors, they are the routes that are eligible to be a backup path. Now, in order to be a feasible successor, in order to be a backup path, they need to meet the feasibility condition. We also have something called the reported distance. The reported distance is the distance that a router, a neighbor router, will tell the router that is interested in calculating the best path what is the distance of itself to the destination network. We also have the feasible distance as well, which is the distance that this router that has the calculation for a network will tell the router that is calculating the best path it can have to that specific network. Routing loops, they are all prevented with this dual algorithm. In order for us to have a loop-free topology, we need to meet the feasibility condition. In other words, the feasibility condition will just basically tell us that the metric that another router tells a certain router needs to be lower than the metric of the router to the destination network itself. If it's higher, that is basically because there is a loop in the topology. In this example here, we have the successor and feasible successor. Now, a successor is a neighboring router with the least cost to the destination network, as we already discussed. So if we have the lowest metric calculation, that is going to be the successor. It has the best way to reach the destination. The feasibility distance is the lowest calculated metric to reach the destination network. The feasibility distance is the second number inside the brackets when you do the show IP route. Now please notice that the EIGRP best path for the 192.168.10, which is the network right here, is through router 3, and that the feasible distance is 3,012,096. Now, if we analyze this, what is happening here? So I need to reach I need to reach this network. Cool. So what is the best path according to EIGRP? Now, as we already checked, EIGRP will consider two things by default, and that is the bandwidth of the link and the delay of the link. Now, because here we actually have a 64 kilobit link, which is lower than the 1024, the chosen path with the lowest metric is the path through router 3. Now, once we calculate these two metrics and we find that the best path is through router 3, we can call these path the successor route. I go directly to router 3. Now, the alternative path would be going to router 1. This is also an alternative path. Even though it's not the best path, it's an alternative one. It could be a backup for us. So if this link goes down, this feasible successor route could be taken into consideration to still reach the network connected to router 3. Now, once the dual algorithm converges, it basically tells us that we have found the best path to reach a destination network. For instance, we can find some extra information about the feasible distance, the successor, and all the other information from the routers themselves using the show IP route command. Now, the reported distance that each neighbor advertises to each destination is called the RD. The feasible distance is that the router would use to reach the destination via that specific neighbor. This is just the definition of the routes that exist, every single one of the routers themselves. Now, the first line in the topology table displays P routes, which are basically passive routes. Now, passive in EIGRP is a bad thing. It's actually a good thing. It means that everything has converged. All the calculations have been done. Okay. So P in EIGRP is a good thing. Now, when we have A, it means it's active. It means that it needs to recalculate every single one of the things. So if we do a show IP EIGRP topology and we see a P character right next to every single one of the networks, that means a good thing has happened. All the networks have converged. We have found the best paths for all the networks according to the dual algorithm. Okay, now the dual topology, we also able to verify the dual topology with the show IP EIGRP topology command. Now, dual works as a finite state machine. It just basically tells us how things work. Okay, so it calculates the best paths. If it doesn't find the best path, it will just try to recalculate again. It will try to reach out to the routers again, and so on and so forth. And then it repeats the cycle until it's finally able to install a route successfully in the routing table. IP EIGRP, as we already discussed, this would be the best path chosen in this circumstance here. However, if this link goes down because we have a feasible successor, we will still be able to send traffic to this destination network. Okay, we already discussed this. There is a packet trace activity for you guys to do once again. It's about the dual finite state machine. Now, before we start with IPv6, guys, I'd like to take a brief break because this is intense. So I'm just gonna pause. All right, now let's talk about how to implement EIGRP for IPv6. Now, there are striking similarities between EIGRP for IPv4 and EIGRP for IPv6. For instance, they use the same IP protocol number, which is 88. So if we actually analyze an IP packet and check the opcode, we'll be able to see that they are basically the exact same protocol number. Okay, we check the headers, they have the exact protocol number. Now the configuration is very similar. The configuration is pretty much the same.
Robert, can you please share
However,
the
when we
screen?
have EIGRP for IPv6, we are not actually going to
Robert?
configure the networks that we want to advertise. We actually do. Oh yeah, sorry guys, I'm gonna share my screen. Don't worry, I've already started recording the screen, so you guys be able to see this later. All right, cool. So EIGRP for IPv6 work pretty much the same way as IPv4. They both use protocol number 88 in the IP packet. Now, they have striking similarities. They're pretty much configured in the same way, except that EIGRP for IPv6 is configured per interface. So you actually have to go to the interface and activate the interface to be part of the EIGRP process. Now for IPv4, we don't actually need to do that. We just need to specify the network under the EIGRP router configuration. One table comparing IPv4 and IPv6 EIGRP. Of course, when we're using EIGRP for IPv4, we want to advertise IPv4 networks. When we are running EIGRP for IPv6 networks, we want to advertise IPv6 addresses. They are both distance vector protocols. They both use the dual algorithm. They both use bandwidth, delay, load, and reliability of the links. They both use the reliable transport protocol to exchange messages. They both use incremental, partial, and bounded updates. They both use hello packets. Uh, EIGRP for IPv4 uses the multicast address 224010, while IPv6 EIGRP uses FF02 colon A. Both of them will support the hashing algorithm SHA and MD5, and both of them will require to have a router ID. Now, please note that the router ID stays the exact same in IPv4 and IPv6. It doesn't mean just because I'm configuring EIGRP for IPv6, I also need to configure router ID which looks like an IPv6 address. That is not true. We actually need to configure a router ID in the same format as the IPv4 address. So that one is still the same thing as well. EIGRP for IPv6 messages, they are sent using source IPv6 address to a destination IPv6 address, which is the IPv6 multicast group address for EIGRP routers, which is the FF02 colon A. The source IPv6 address of the router for the packet will be the link local address of the exit interface. So keep this in mind because we actually have the global unicast address as well in IPv6 networks. That is not going to be the one used by EIGRP for IPv6 to be the source of the packet. How does the configuration works? Like I already said, pretty similarly, you have to define the EIGRP. However, we need to tell that the interface needs to be part of EIGRP v6. In this example here, we are actually doing the basic config on all the routers. We are assigning an IPv6 address on every single one of the router interfaces. In router 1, I'll go to gigabit 00. I'll set an IPv6 address for that interface. I'll do the same on the serial connections as well. Keep in mind that whenever we have a DCE, digital communication equipment, we have to specify the clock rate in one of the ends of the serial connection. In this case here, router 1 is going to be the DCE for serial 000, so I just need to set the clock on this interface. I don't need to set the clock here on router 2 because I already done this in router 1. Now this applies to every single one of the other serial links as well. Now, after configuring IPv6 addresses on all the interfaces, It is just a matter of also assigning a linked local address to the interfaces as well. So we go to every single one of the interfaces again. Now this time we're actually going to type it in the keyword linked local in the end of the IPv6 command in order to make sure we are configuring a linked local IPv6 address. Now that we configure IPv6 addresses on all the routers, now that they can communicate with themselves, it is just a matter of, first of all, enabling IPv6 on every single one of the routers with the command IPv6 unicast routing. So we go to every single one of the routers, type it in IPv6 unicast routing, and that is going to enable IPv6 on every single one of the routers. So if you remember from routing and switching, this will actually do something very special. It will activate the router advertisements on every single one of the routers. In other words, it will activate a router to be running IPv6. After that, it's just a matter of configuring EIGRP. We do it in a very similar way that we do IPv4 EIGRP, except that now when we define EIGRP, we are going to specify that it's IPv6. So we type it in the command IPv6 router EIGRP. Here we are going to define an autonomous system number saying that all of the routers, they are managed by the same organization. After that, we need to manually assign an router ID to every single one of the routers. If you guys remember, when we were doing EIGRP for IPv4, this step was actually optional. Because when we have IPv4 networks, a router can assign itself an IPv4 address to be the router ID. Now, when we only have IPv6 addresses, the router is not able to do that. So if we forget to assign the router ID and we don't have any IPv4 interface on the router that we want to configure EIGRP for IPv6, it is not going to work. We actually need to go to the router itself and set in a router ID manually, or at least we need to have one of the interfaces with one IPv4 address. Now, by default, EIGRP for IPv6 process is in shutdown state. We also need to type in no shutdown for the EIGRP process as well. So once we define EIGRP, once we set the router ID, we need to type it in no shutdown for the EIGRP process. Unlike EIGRP for IPv4, which uses the network command, as already mentioned, the EIGRP for IPv6 is directly configured on the interface itself. So we need to go to every interface we want to make part of the EIGRP process and type it in the command IPv6 EIGRP and then the autonomous system number that we defined for the EIGRP process. Of course, we can also create passive interfaces if we want to. Now, setting a passive interface doesn't mean the interface is not going to be advertised. Remember that the passive interface will influence if the interface will form a neighborship. It has nothing to do with the fact that you can still advertise the network connected to that specific interface. In this example here, we have gigabit interface 00 as passive. That just basically means I will not be sending hello packets out of this interface because I will not have a router there. It's a local area network. That doesn't mean I don't want to actually advertise this network because I want all the other routers to know about this network. So I still need to go to the interface itself and I still need to tell that this interface needs to be in the EIGRP table. So I still need to go there and specify IPv6 EIGRP and then the autonomous system number. That step is still necessary. A few commands we can use to verify EIGRP for IPv6. We have the show IPv6 EIGRP neighbors, pretty much the same as the show IP EIGRP neighbors for when we're configuring EIGRP for IPv4. It shows information about the neighbors. It shows which interface is the neighbor connected to, the hold time, the uptime, and so on. We also have the show IPv6 protocols. It's very similar to show IP protocols. Now we are just displaying information about the dynamic routing protocols that are advertising IPv6 information. Basically the same thing. It will show the metrics, it will show the router ID, it will show the distance, it will show which interfaces are part of the EIGRP process. We also do have the show IPv6 route. It will display all the learned routes through EIGRP. Once again, they will all be displayed with a D right next to them because EIGRP for IPv6 still uses the dual algorithm to calculate the best paths. There is one packet tracer activity for you guys to do to study EIGRP with IPv6. One more lab. And we're going to do the chapter summary. After that, we're going to do the demo. There is a skills integration challenge for you guys to do. And this is all the topics that we discussed today. We talked about EIGRP. Now, EIGRP is a classless routing protocol, so it doesn't matter the class. Okay, it can use subnets. Doesn't care about it. It uses the dual algorithm to calculate the best paths. It has an administrative distance of 90 for internal routes and 170 for external routes. It uses the reliable transport protocol. It has partial and bounded updates, triggered updates, so we just basically send an update whenever it's necessary. It's not periodic as RIP. It can use equal and unequal cost load balancing. So it doesn't actually need to have a best path. It can have multiple best paths. These all paths can be active at the same time. EIGRP uses protocol-dependent modules. That basically means EIGRP can work well with IPv4 and IPv6 networks. We also discussed about the message types, the hello update, query reply acknowledgement. We said that the hello message, they don't need to be acknowledged. But we also said that the updates, the queries, they are reliable transport and they also require acknowledgements. Now we talked about how to troubleshoot EIGRP, some basic commands to do that. We have the show IP EIGRP neighbors to verify all the neighbors. And we also discussed about the algorithm itself, about the formulas that are related to the dual calculation of the metric, and how does EIGRP chooses the best path based on the lowest metric. We also discussed about how an EIGRP router can also become a backup route for when a certain link fails. We also talked about how to configure EIGRP through the router EIGRP command and the network command in order to advertise certain networks. We also discussed about how to do that with IPv6 EIGRP. All right, cool. So this is all the theoretical content we had for today. Now, in order to finish this class before we actually call it the day, we actually going to do a demo. So I'm going to take the packet tracer that we have done last week, and we are actually going to make this work using EIGRP. I'm going to erase this. So this is going to be what we're going to be doing. We're going to configure EIGRP for IPv4 to be able to learn all the networks on all the routers. So this is what we want to accomplish. On all the routers, we want every single one of the routers to learn about all the other networks, even though the networks are not directly connected to them. This is exactly what we're going to be doing here in this demo. Now, this has been already configured with what we configured last week. So if I go to router 1, CLI, can anyone tell me what is the command to verify the routing table on router 1? Type it in, guys. From the global configuration mode, how do I verify the routing table in router 1? Anyone? Come on, guys, wake up. We're nearly done. Do show IP routes, okay? Now, if we analyze this table, we basically see that router 1 is unaware of network C, and it's also unaware of the peer-to-peer connection to the internet. So we want to learn about these two networks. In order to do that, I'm going to configure router 1 with EIGRP. I'm going to configure router 2 with EIGRP as well, okay? And then we'll see what happens next. Okay, so what is the command for me to configure EIGRP? Anyone? I know we just studied this, but come on, you can try this. Router EIGRP, okay? This is the command in order to configure EIGRP. We use a question marker here. It's actually going to tell us we need a number for the autonomous system. So I'm going to set it to 100, just as an example. Router EIGRP 100, it's going to be my router autonomous system. Now, how do I make sure this router will be able to advertise this network and this network? So I have already configured the interfaces, and we can clearly see here the router already knows about these interfaces. Now it's just a matter of telling which networks I want to advertise. And I do that with the command network. Now we can configure the router ID if we want to. Now, just like I said, it's not compulsory because we do have IPv4 networks. We do have IPv4 addresses on the interfaces. So we are not forced to do that in order to make things work. Now I'm going to do that just because it's much nicer. Okay. So let's set the route ID here. Route ID. So what do you guys want to give here? Let's use the question mark for help. Oops, it's actually EIGRP router ID. Okay. So with the command EIGRP router ID, I'm going to be able to set a router ID on the router. Cool. Now we need to tell the interfaces we want to advertise, the networks we want to advertise. Can someone help me out here? How do I do this? I want to advertise network A using the EIGRP 100. I'll type it in the command network, and then I can specify the network 192.168.10.0. Okay. Now if I do a space question mark, it's actually going to tell us that he wants to know the wildcard bits. Can anyone tell me the wild? Yeah, thank you very much, Nipes. 000255. Cool, done. How about network B? How do I make sure I'm going to advertise network B? Anyone? Same way. 192.168.20.0. Oops, sorry. Done. Is there any other network I need to advertise? There is this one as well, right? So I want to advertise this information as well. So I'm going to advertise that network as well, just in case. 10.1.1.0. What is the wildcard mask here, everyone? /30. Anyone? Yep, perfect. Thanks, Nicole. That's it. So now we're pretty much advertising everything that we know of in router 1. Now, the extra step that we're going to do is we are going to configure gigabits interfaces on router 1 to be passive interfaces. Because I don't want router 1 to be sending hello messages out of these interfaces because they are connected to a local area network. So how do I do this? Anyone? How do I make sure router 1 will not send any EIGRP hello messages to the LAN interfaces? Yep, with the passive interface command. Exactly. So I'm going to go passive interface. And I'm going to type the interfaces. 000 in this case, and also 001. Cool. Done. You can go exit. Now that we have configured EIGRP on router 1, we can save the router config with a do w1. Okay. Now, does anyone remember what is the command to verify the routing protocols that I have just configured? Come on, guys. Show IP protocols, right? Now, because I'm in global config, I'm just going to type in do show IP protocols. And check it out. This is just everything that we have just done. So router 1 has been configured with EIGRP 100. Okay. We have the metrics. We have the hop count, the maximum hop count, the variance. We have redistribution. We have maximum paths. We have the routing networks. So these are the networks that are going to be advertised by router 1. And these are the passive interface that I have just configured in router 1. Okay. I also have the administrative distance, which is 90 and 170 for internal and external routes. That's pretty much what I have. Now, if I want to check the neighbors, what is the command for me to verify if I have neighbors? Come on. Do you guys remember the lecture? Show IP EIGRP neighbors? Yeah. Show IP EIGRP neighbors? Yeah. So if I go, I'm in global config, so I want to force this command. Do show IP EIGRP neighbors. Okay. As we can clearly see here, there's nothing. Does anyone know why there's nothing? I haven't configured anyone else. I just have one single router. It cannot form a neighborship with the other router because the other router hasn't been configured with EIGRP. So let's configure router 2 with EIGRP and see what happens. Go to router 2. Anyone guide me through the process of doing the same on router 2? How do I configure EIGRP on router 2? Anyone? Let's go. So let's go to global config first. Enable conf t router EIGRP 100. Okay, it has to be the same autonomous system number, otherwise they won't be able to talk to themselves. What else? Let's set up a router ID as well. It's going to be 2.2.2.2. Oops, EIGRP router ID, sorry. And now we just need to specify the networks that we want to advertise. So let's go ahead and advertise every single one of the networks that we have connected. So I'm going to advertise network C. So 172.16.0.0. Does anyone know the wildcard mask for /16? Anyone? Yep. Perfect. Done. Now, how about the other networks as well? Network 10.1.1.0. What's the wildcard mask? Yep. How about the other one? The one that connects to the ISP? As we see here, check it out. We've got a message. Oh, we found a friend. You found a friend in need. Yeah, so now we are friends with router 1. Okay, so we have sent a hello message to router 2. Router 2 has replied to the hello message, and then they now friends. Okay, they can exchange information. Now, there's still one more network I need to advertise in router 2, which is the peer-to-peer network. So let's do that. Agree? Yeah. And now how about the passive interface on router 2? Which interface on router 2 should be passive? Anyone? Which one of the interfaces in router 2 should be passive? Now the answer to this question is the same answer to which interface of router 2 connects to a local area network is gigabit 000. So let's go ahead and passive interface gigabit 000. Okay, that's it, done. Now we can save the config with do WY. How do I verify the dynamic routing configuration on router 2 to make sure I have done the right thing? Anyone? Yep. Do show IP protocols. So same EIGRP autonomous system number. These are the networks that I'm advertising, and few extra information as well. This is the passive interface that I have just configured. And what else here do we have? And we also have a source of information, which is router 1. So it's already telling us that there is a source of information that is coming from router 1. Now, let's verify the neighbors. Cool, we have a neighbor. Okay. Who is our neighbor? 10.1.1.1 out of interface serial 010. I'm waiting for 10 seconds for another hello that comes from router 1. And this is the uptime. This is the amount of time that I have been friends with router 1. And this is the amount of time we've been communicating. Now, how can I verify if I have learned the routes from router 1? Shai has already typed the answer, is verifying the IP route. So I'm going to type it in do show IP route and see what do I have. So what do I have in here in the bottom? Anyone? What is this? What is this? Does anyone know what this is? These are the two networks that I have just learned through the EIGRP process, and I can tell that because it's a D route. Okay. And how do I get to this network? I need to go to 10.1.1.1. In other words, if I want to reach network A, it is just a matter of sending a message to router 1. This is exactly what these entries telling me, guys. The same thing for network B. If I want to send a packet to network B, how do I get there? I get there via 10.1.1.1, which is just basically router 1. So you guys remember that the routing table is just networks, and how do we get there? This is exactly what we have here, both routes that we have just learned through EIGRP. Now, let's go to router 1 and verify if router 1 has learned about all the networks connected to router 2. How do I verify that? Do show IP route as well. How many routes have we learned from router 2? So we have learned about this 10.2.2.2, and we have also learned about the 172.16. My God, but I thought we were going to learn 3 routes for router 2. Why do we only have 2? Because router 2 already has the peer-to-peer route. Okay? That's it. So it just needed to learn about network A and network B. This is all good. It's correct. That is great. So now my quick question to you guys is, now that EIGRP has been configured, The routes are being learned. Am I able to ping from PC0 to PC2? Finally able to do that? Because remember, when we were doing this last week, we couldn't do it. And we discussed about why we couldn't do it. Now we are going to be able to do it because after all, router 1 already knows about all the networks. Router 2 already knows about all the networks. Now everything should be functional. So let me take IP address of PC2. So it's 172.16.01. Now let's try to do these tests. I'm going to go to PC0. Ping 172.16.0.1 and let's see what happens. Might take a while. Yep, we're all good. So now we can ping from PC0 to PC2. Now how about the opposite? Let's try to do the opposite. Yep, all good. Perfect. Now this is working. So now I can just basically ping everywhere. Cool. Clear. So all of our network is connected. We're able to ping between different networks even though they are not connected to the same router. Okay, that's all we needed to do, guys. So yeah, this is just a quick demo showing you guys how to actually configure devices using EIGRP. Now, Wednesday we have a Cisco lab. In the Wednesday Cisco lab session, I'm actually going to record a demo by configuring EIGRP for IPv6. All right, so I'm gonna post this video on Wednesday. Make sure you stay tuned. Make sure you watch the video as well to learn how to do it. And that's pretty much all.